Hello everybody, we are going to be going over our 1.7 notes, inductive and deductive reasoning. I just have inductive reasoning on here for some reason, but whatever. Okay, so what we're going to be talking about today is the ability to look at a pattern and based on the pattern that we are looking at, come up with a conclusion and use that conclusion to maybe find more things within that pattern, okay? So one of the important vocab words today is conjecture, and a conjecture is an opinion or conclusion based on incomplete information. So everything that you're going to be given today is going to be, for the most part, incomplete, and you're going to have to make a hypothesis based on that information that you're seeing. So the first picture, oh, by the way, before I get started on this, pattern recognition is probably one of the most important things that you as a human being can have, okay? People that have pattern recognition tend to do a lot better in life, and I know that sounds weird, but it's important. It's not, I don't want you to look at this and be like, why are we doing this? This is weird. Because you have to be able to find patterns in the real world. That is how you are able to problem solve, and just know that you being somebody who can pick out patterns and do things of that sort, you're going to be very valuable to the workforce, okay? So, moving on. Number one says, describe how to sketch the fourth figure in the pattern. So if you look at each of these figures, look at them, take a second, think to yourself, what do I notice? What do I see? What is a conclusion I can make just based on what I'm given here? And when you look at each of these things, in the first step, we have two boxes. It goes gray and then white. When you look at that second step, it's almost as though the number of gray and white tiles has doubled because we started off with one gray and one white, and now we have two gray and two white. And then whenever we go over to this third picture now we have four gray and four white. So again, it's doubled. So what do we think that fourth picture might look like? Okay, that's what I want you to do. I want you to describe how to sketch that fourth figure in the pattern, okay? We're going to move on to number 2. It says, describe the pattern in the numbers 1,000, 500, 250, 125, and write the next three numbers in the pattern. So what does it look like is happening in this pattern when you're going from 1,000 to 500, 500 to 250, 250 to 125? Hopefully you're saying to yourself, oh, it's being cut in half, okay? So if this is being cut in half, then what I need to do is I need to take 125 and cut that in half so that the next three terms, okay, this next term is going to be 62.5. I got to cut that in half. That's going to be 31.25. I got to cut that in half, and that's going to be this gross number, 15.625. So we're recognizing a pattern and then being able to do something with that pattern. Okay, this is one of my favorite things to do. Use the table to the right. What pattern do you see? Hint, look at the last term. So what I want you guys to focus on in this problem specifically is the last term in each of these numbers here. We have 3971, 3971. So without knowing anything about the first numbers in each of these terms, what do you think the next ending number is going to be if we look at x to the 9th power? Hopefully you would say it's going to end in the number 3. The numbers in front don't matter, but it's going to end in the number 3. Okay, so based on that, I know that I have a pattern of 4, 3971, and then it starts again, 3971, and then if I were to repeat it again, it would be 3971. But there are 4 numbers within each of these patterns. There's a 3, a 9, a 7, and a 1. And we're going to use that to help us figure out numbers 3, 4, 5, and it's supposed to be 6 over here. Number 3 says, what is the last digit of x to the 15th? Well, could you count all the way down to x to the 15th and figure it out? Sure. But look at this. Number 6, what is the last digit of x to the 313th power? I don't think you're going to want to count all the way down. So there is a cool little trick that we can do when we know how many numbers are in a pattern and use that to help us figure out the last digit of each of these x to whatever the power is. So what you're going to do is you are going to take the exponent that you are given and you are going to divide it by the number of items within your pattern. There are 4 numbers within our pattern, so we're going to do 15 divided by 4. And when I do 15 divided by 4 in my calculator, I get 3.75. That's important. The 3 in the front tells me that I'm going to make it 3 whole ways through my pattern. So I've got a 3971, a 3971, and then another 3971. This 0.75 tells me how many leftover numbers I have until I get to the next full pattern. Well, 0.75 is 3/4. So when you look over here, this will be 1/4, 2/4, 3/4, 4/4. So if this is 3/4, that means that after the third full way of making it through my pattern, I'm only making it 3 terms out of the 4 terms this next go around. That would mean that my last digit is going to be 7, because that is the third term. Let's do it again. Let's look at 118. So we're going to take 118, divide it by the total number of items within my pattern, which is 4. We've got 118 divided by 4, and that's going to get me 29.5. That means that I'm going to make it 29 ways through my pattern totally. This 0.5 is what I have left over. Now, 0.5 is, 1/2, but for us, it's going to be more helpful to say that it's 2/4. Well, 2/4 is here. So my ending number would be 9. My ending digit would be 9. All right, and then we've got 200, so we're going to divide that by 4. I think that's going to give me a whole number. 200 divided by 4 is 50, which means that I'm going to make it 50 ways through my pattern, and I'm not going to have anything left over. So what's the last number in our pattern? That last number in our pattern is 1. And then lastly, we have 313 divided by 4. And we are left with 78.25. 0.25 is 1/4. So I'm going to come all the way up here, and that's going to be the last digit of 3. And that's how you complete a pattern like this one. This one might be hard without any kind of guidance, but that's essentially what's happening here. All right, number 6. We've seen these problems a lot. This one's a little bit different, but it's not super different. Okay, it says Martin arranged some cans in a triangular pattern on a table. The top row has 1 can, the second row has 2 cans, the third row has 3, and so on. The arrangement is shown below. Which equation gives the total number of cans in the arrangement when the cans are stacked in rows high? So we have to be careful with the way this problem is worded, because it's not just asking us like how many cans are in this row, because that's easy, we can see it. The difference is when you have 4 rows, 1, 2, 3, 4, how many total cans do you have? So what I want to do is I want to make a table, and I'm going to put we're going to do row number and then total cans. Okay, and we're going to make this table to kind of help us out. In row 1, how many total cans do you have? You have 1. Now, once you add on row 2, how many total cans do you have? You have 3 total cans. Whoops. When you add on row 3, how many total cans do you have? 5. When you add on to row 4, how many total cans do you have? 1, 1, 2, 3, 1, 2, 3, 4, 5, 6. Oh, help if I could count. I was like, something looks weird to me. There we go. 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then when I add on my last row, row 5, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 15, okay? So what we need to do is we need to figure out which one of these equations my row number is going to be in and my total cans is going to be T. And I always look at the last option just because it's the one that will usually only work for these. Sometimes if you use the first option, that 1 and 1, a bunch of these will work, okay? So I always look at the easy one first, B. All right, so this one says, that's not going to work on this one because it's going to work, but that's not the one that we need. We're going to try each of these. So this should be 15 is going to equal 5 times 5 minus 1 divided by 2. That's going to be 4 times 5 is 20. 20 divided by 2 is 10. So this is 10 equals 15. That's not going to work. T is 15. That's going to equal 3 times 5. That does work, but we can't stop there. We got to keep working. 15 equals 2 times 5 plus 1 divided by 5. That's going to be 6 times 2 is 12. 12 divided by 5 is definitely not 15. All right, we got 15 equals 5 times 5 plus 1 divided by 2. That's 6 times 5 is 30. 30 divided by 2 is also 15, so that one also works. So we're going to have to look at a different number here. 2 times 5 and then 5 minus 1. This will be 15 equals 10 times 4, which is 40, which is not what we want. So let's pick another one. Let's do 3 and 6 and see if that works. So 6 is going to equal 3 times 3. That's 9, so that's not going to work. So it must be D. That's the one that's going to work for this one. Number 7, it says, make and test a conjecture about the sum of any 3 consecutive numbers. So what that means is I could do 1 plus 2 plus 3. I get 5. Let's pick 3 other consecutive numbers. Let's do 24 plus 25 plus 26. That's going to be something that I don't want to do in my head. 24 plus 25 plus 26 gets me 75. Let's do 101, 100 and no, let's not do that one. Let's do 97, 98, 99. These are all just 3 consecutive integers. That gets me 294. 97, 98, 99. So we would have to think of a conjecture and decide whether or not our conjecture is true based on any patterns that we're seeing. I'm not super concerned about that one, so I'm going to skip through it. All right, this is another important section. This is our counterexample section. A counterexample is a specific case that shows a conjecture is false. So remember, a conjecture is you making a hypothesis over what you think might be true, okay, or just guessing what might be true. It says find a counterexample to disprove the following conjecture. So this conjecture says the value of x squared is always greater than the value of x. So for example, if I picked the number 2 for x, then 2 squared is 4. Well, in that case, x squared would be greater than x, right? So we need something to show that that's false. So is there any number or even numbers that you can think of that would prove that conjecture to be false? The easiest ones in my mind would be 1. If x is 1, x squared is 1. Is that going to be greater than 1? No. 0 would be the same thing. So that would be a counterexample. Here's another one. If x squared equals 25, then x equals 5. This one might not be as obvious to you, but what else can I square other than 5 that will get me 25? Well, the answer to that is negative 5. Because isn't it true that negative 5 squared is also a positive 25? And then here's my favorite one. If a polygon has 4 sides, it is a square. Well, what other shapes do you know that have 4 sides other than a square? You got a rhombus, you got a trapezoid, you got a kite, you got all these other kind of things. So you could just make one up. I'm just going to say rhombus. You could have said something crazy. I don't know. Anyways, so that's what a counterexample is. It's you taking a conjecture and you being able to find an example to make that conjecture false. Okay. All right, this last part is a review. I'm going to skip it. I'll have the answers for it on the completed review, but I'm not going to have it in the video just for the sake of time. Anyways, if you have any questions about conjectures, go ahead and go talk to your teacher during their normally scheduled tutorial times, and I will see you in the next video. Bye.